Great. Any other questions on the project or on the project proposed? Damn, this is very loud. Is it usually this loud? No. Volume down. Test, 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 test. Test, test. Better. Great. Questions on the project proposal, which is due tonight, or on the assignment number 4? Yeah. You might, I'm not sure. Yes, I think you should get feedback, but like I wouldn't, I'm not sure if you'll get feedback in time for like changing assignment 4 like significantly. So for your simple project, for your simple experiment that you're proposing, you probably just want to make sure that it's tractable. It's also fine if like the experiment, this is way too loud, I don't know what's going on. Sorry, I'm going to figure this out. Volume down, volume down, volume down. Okay, so now it's basically almost perfect. Okay, let's roll with this. Yeah, so no, you will probably get feedback before then, but I wouldn't guarantee that it's going to be 2 weeks before the assignment number 4 is due. Yes, you should. Well, I mean, unless no one has ever done something like it before. Yeah.
I think what the section says, like, what is your approach at, like,
yeah.
But if you're like implementing something, a model that exists, like, how do you?
Then you just you don't have to specify in that case. Yeah. Maybe or you can say the thing that is new is that I make it tiny. Like, you know, that's also a fair assessment. Okay, cool. Then we can get any other questions. Great. Then we can get started. Today's class is on motion and objectness, or rather on motion and objectness, the first instantiation of that. So let's talk about that. So why is this important? Or like, why are we talking about this in the first place? You might have noticed that so far we've always talked about 3D reconstruction and like 3D representation learning, but conspicuously all of the things we've talked about handle only static 3D scenes. Which seems kind of a major limitation because many times the things that we are interested in are actually dynamic things. So I will say that even if you only deal with static scenes, it is still exceedingly useful for tasks like, for instance, in robotics. Even though your robot might be manipulating a scene maybe, oftentimes in robotics, many of the problems that are still unsolved are quasi-static, so stuff only moves when the robot moves something. And so that allows you, for instance, to say, okay, I'm going to take an action, then I'm going to reconstruct the scene again, and then I plan my next action, and then I take it. So it's like, it's reasonable to do that. But the moment something is not quasi-static, which means that the moment, quasi-static means stuff only moves when your robot takes an action. The moment stuff moves by itself, then all of the methods we've discussed so far are kind of useless, because the moment stuff moves by itself, you can't actually reconstruct it in 3D anymore. So that's why we have to eventually branch off into this area of dynamic 3D reconstruction. And dynamic reconstruction is really is something we cannot do robustly today. So I can just state that up front. So the stuff that we're learning now is like the first. So it is interesting that this has been a very long-standing problem. In the past, it hasn't worked at all. Like 10 years ago, there were like some papers, like Dynamic Fusion in 2015, for instance, was a great paper, or 2007, that basically did like 3D reconstruction from RGBD video in like a very constrained setting. So these approaches existed, but it didn't actually work. So like there was certainly no method 10 years ago where you could take a video with a camera and then you can get a dynamic reconstruction, like a scene, like a 3D reconstruction of a dynamic scene. That just didn't exist. And by and large, that still doesn't exist today. So like if you take a camera right now and like you walk through like a crowd, there's no method on the whole planet that can give you a 3D reconstruction of that scene right now. It's just not something that's possible. But we are getting there. So like it is also true that the techniques we've talked about in the class so far have enabled a completely new perspective on this problem, as we'll see today, to a degree where now I would predict that this is also one of the things that will be feasible in the short term. Like not in the most general case, maybe. So not in the most general case, like you can always do it, but certainly in the case like, there's a tabletop and the robot is manipulating something and you want to dynamically reconstruct it. I think these kinds of things will be possible in the near future using the techniques we discussed in the class. Which is very exciting, like differentiable rendering and like prior-based reconstruction and some of the things we're discussing today. Cool. So many of these slides are from Shubham, who is great at CMU. If you see him, say hi. We live in a dynamic world. This slide I stole from Shubham, and I actually put it into a lot of my talks because you can't make a better slide than this. Check this out. It's just cats and sheep. They're all having fun. So basically, stuff moves all the time. And I mean, it's actually very impressive. This sheep, right? This sheep clearly is having fun. And the sheep is actually, you would guess, like, I don't know that it has a very good model of the trampoline that it's jumping on, but like it kind of clearly has some idea of what's going on. It understands that when it's jumping up and down, something funny is happening. So even the sheep has a scene representation which far exceeds any robot that we can build today, which is, sheep aren't known as the most intelligent animals in general, but they're very intelligent compared to everything that we build today. So these are obviously not maybe particularly useful situations, but of course, as we just discussed, many useful situations have dynamic components in them. And in the frameworks that we have discussed today, like let's say we take the framework of NeRF, or like, we always discussed about neural fields and field representations in general, and we always said, what is a field? A field is a function that maps a space-time coordinate, like a space-time coordinate to whatever is at that space-time coordinate. So you might be compelled of saying, okay, how is dynamic 3D reconstruction different from static 3D reconstruction? Maybe it's not different at all. You're just going to take our NeRF, for instance, which here is parameterized as 3D coordinate x, omega in this case is the view direction, right? Like the view direction for like view-dependent effects, x omega t. Then we have a neural network, and that maps it to a density and a color. And so now if we have a video where stuff is moving, we get the camera poses, which is hard. If the scene is moving, it doesn't actually work all that well, but with a lot of hackery, you can get it. So you take a video of something that's of a dynamic scene, you get the camera poses, and then you just try to reconstruct a field like that. Note that this is, in this case, a NeRF, so in this case, it's a neural field, but of course, in the general case, right, you can also say that this is just a, this doesn't have to be a neural field, it could also be a voxel grid. In the case of a voxel grid, right, what would it be? It would be a 4-dimensional voxel grid. You have like 3 coordinates x and then another coordinate time. And all of the things we discussed about hybrid representations and stuff, all of these different ways of parameterizing these functions still apply. So in fact, there's papers we might discuss in the next lecture that basically take what's the generalization of a triplane to XYZ time. Well, you might guess, maybe now you have 4 planes instead of 3, or maybe you have several triplanes over 10, you can do whatever you want. So, Okay, so let's do that. The problem is that that actually doesn't work in the general case. So let's think about why that doesn't work in the general case. Imagine that some part of the scene is staying, like the problem is fundamentally that like the inductive bias or the kernel that you have for this, like in the case of the neural field, is really not in jam with the function that you're approximating. So for instance, for 3D scenes, right, we've discussed that neural fields, for instance, have this like kernel that is basically like interpolating according to some notion of locality. So if you have these positional encodings, for instance, the notion of locality is the Gaussian kernel, right? Do you remember that? Positional encodings and siren, yeah? The problem is if like a scene is static, and I'm filming the static scene, but now the time is continuing, right? Like your input to your neural network will continue, the time will increase, even though the scene doesn't change. So like the coordinates of like this point over time will change a lot because like in time, right, like this, even though the scene stays static, the time coordinate of this point goes on and on and on and on. So like this really seems like not such a good, it doesn't really capture the locality of like scenes in space-time very well. So you could do it with like, we could do it with like generalization, where we would basically hope to say, okay, maybe we can capture we could instead say we do it with generalization. In fact, there is a bunch of methods that do that. So instead of having the time variable be something that continues over time and it's just an input to my neural field, maybe instead we say that for each time step we have a little latent code. and then you do something like auto-decoding. Remember like the auto-decoding thing where we say we have like this latent code, and the latent code basically parameterizes this, for instance, the shape of the space of cars. Now you can say maybe I have different latent codes for different poses, but even though the human moves over time, the different poses can be captured by like different latent codes, and so you can share information over time. And that is something that has been done, and that is like a reasonable thing. But in fact, it also doesn't quite capture it. One way to say this is that none of these approaches actually capture the actual geometry of what is going on in space-time. So like specifically when I move across time, right? There's physics going on, and physics basically tell you how every point of my body moves over time. And none of these approaches kind of model that explicitly. And we've done all this effort of modeling the physical process of light transport and of 3D so carefully. And now seemingly with these approaches, we just throw all of that out the window and we don't do any modeling with respect to like how stuff moves. So that's not optimal. And in fact, if you try, and that is in fact the reason, then if you try to do this, this doesn't actually work. So in fact, because you are, as compared to what we did for 3D, where we did all of this careful modeling with like differential rendering and modeling the geometry and how light moves, if you just do this naively and you just stuff an additional input as a time variable in, I don't know if I have a failure case in this case, but it actually doesn't work. So let's think about what actually would happen. So let's say we have a camera and we're like, let's say we had a static scene and we had the camera and we moved the camera over time. We would get the camera poses, then we could just reconstruct the 3D scene using differential rendering, no problem. Now let's say the scene also moves, and now we basically move the camera over time. And now for every time step, like for every frame, we also have a time step associated with it. What you will find is that you can re-render each of the views that were in the training set, but the moment you move the camera, everything will break. So if you just do this naive approach where you just give your neural field x by z as input plus the time, then the reconstruction won't work, because for each time step, you haven't seen multiple observations of each object. For each time step, you've actually only seen one observation of the moving object, for instance. So like if an object is moving, for each time step, you only see that object from one perspective. This would work if you had like a lot of cameras. If you had a lot of cameras, and for every time step, you would have multi-view, then you could think about this problem like for every time step, I'm just reconstructing a nerve, and then it would totally work. But this is not the case we have in the real world. In the real world, we usually have like one or maybe two cameras, and we have like, and the scene moves, and we need to reconstruct the scene. And of course, if you knew how points were moving over time, then it would work. Let's talk about that. There's this notion of like persistence in scenes, which is basically getting at the geometry of like how dynamic scenes behave, which is that over time, usually in our world, like stuff doesn't disappear and then reappear again, right? When I walk around, basically every point on my body stays persistent. It just moves over time. And so this is actually the geometry that we want to get at. The geometry that we want to get at is that the scene at time step t100 is not a completely different scene. It is instead the scene probably at time steps t, and then it's just moved over time, unsurprisingly. So like the geometry in the scene should be very similar up to like, for instance, non-rigid deformation. Or if the scene, imagine the scene is just consisting of like rigid objects that are moving rigidly, then this constraint is even stronger. The scene at time step t is identical to the scene at time step 10, up to local rigid motion, like a few parts of the scene move. So we are going to first formalize this notion of the notion, like we're going to model what motion means in 2D with optical flow and in 3D with scene flow. And then we're going to see how we can enforce this geometric constraint that we're going to get in the framework of differentiable rendering that we've discussed so far. And we're going to discuss some papers that do that. And then we're going to also discuss the notion of canonical 3D reconstruction, which is basically this idea that I just discussed as a specific implementation. Okay, let's get into it. So let's first talk about optical flow. I was a little shocked when I asked in the classroom last time, who knows what optical flow is? And like a bunch of people didn't know what optical flow is, which is totally reasonable, but now we're going to discuss it. So already back then I explained to folks what is optical flow. Optical flow is basically the notion of motion in 2D. So optical flow tells you if you have a video, like these are 2 frames of a video, and because it's like maybe 30 FPS or so, the video barely changes, but you can actually see that the hand raises, right? The hand goes up and the head pops up a little bit. Maybe the camera pans a little bit. optical flow tells you, for instance, how every pixel in frame 1 moves to every pixel in frame 2. Make sense? So formally, optical flow is a 2D flow field, which means every 2D coordinate is mapped to a 2D offset. So it's a function that maps from R2 to R2. There is the concept of forward optical flow, which tells you for every pixel in frame, like the notion of forward optical flow says, for every pixel in frame 1, so for at time step t, where does it go in time step t plus 1? So that's called forward flow. And then there's the notion of inverse or backward flow, which tells you for every pixel in frame 2, where did it come from in frame 1? Nothing fancy, right? Does that make sense? Great. So that's also a 2D flow field. And then using that, we can just like formalize it. And the thing that I think I want to point out is, so an image, you can see it as a function that maps a 2D coordinate to a 3D color, right? So it's a function that maps R2 to R3. So if you can write an image like a function like this, right? So an image is a function that maps a x coordinate to a color. Then a 2D flow field is also a function on R2, which takes an R2 pixel coordinate and maps it to an R2 flow. So for instance, you could say phi of x maps x to delta x, like how much does x move? And then this notion of like, using that, we can explain a notion of, we can say we render frame 2 from image 1 via warping according to the flow field. So we can basically say we're going to flow every pixel according to the offset. So this works with inverse flow particularly well. So we can say at every pixel, right, at every pixel in frame number 2, so this is maybe frame number 2, we say you can get the color of that pixel by going into image 1 and querying image 1 at the coordinate, at the x coordinate plus the inverse flow. So this is the function that tells you for every pixel where did it come from in the other frame, right? So I don't know, for this thing, it comes from here. Make sense? Great. Yes?
The warp again is the color shouldn't be the same between the two pixels, even like corresponding, right? Because like view effects and things like that can change the color of pixels.
Right. So this is making assumptions. So like the assumptions that you're making is that so the question is, this shouldn't be like the pixel color won't be identical, even if like they are corresponding, or it doesn't have to be identical because of lighting changes, because of view dependent effects, or in fact because of disocclusions, right? So even here in this example, there is, for instance, I don't know, there's, for instance, what's the point? I don't know, you can find points in frame number 2 that weren't visible in frame number 1. So for those points, clearly the optical flow is ill-defined. There's no pixel in frame number 1 that you can find that would explain the pixel in frame number 2. And this is something we're just hand-waving. So in fact, optical flow doesn't have an explanation for this. So what you, for like changing of view-dependent effects, you can just still say that these pixels should be more similar than two randomly picked pixels, right? So then you can just say the metric is like robust to these kinds of things. For disocclusions and so on, there's just nothing you can do. There is just no. So for that, you would have to go to 3D scenes. Like, okay. Any other questions? So this is very basic, but I think it's good to discuss because now it's going to get less basic because we're going to talk about something slightly more complicated. Good. Because now, so just to explain this, right? So this is maybe worthwhile explaining. Let's say we wanted to warp over several time steps. So we want to say, we want to explain, actually, whatever we're going to, so let's say we wanted to explain image number 2. So we had like several frames. So we have this image I2 over here, and we want to explain image I2 in terms of the image I0. Then you can, of course, say, okay, I1 is basically this using the inverse flow that goes from image frame 1 to frame 0. So this makes sense. And then, of course, I2 is I1 queried at the position that is given by the inverse flow. But then you can, of course, explain image number 2 as a function of image number 0 as well by integrating the flow backwards, right? So long story short, you can of course do this for more than single frames if you integrate the flow backwards. But of course, the longer the time horizon, the more the scene changes, and the less you might be able to explain using the pixels from frame 0 versus the pixels from later. And actually, we've discussed this problem before, or like problems that arise to this warping stuff when we talked about self-supervised monocular depth estimation. We talked about all these tricks that these authors did back then. Maybe you remember with like dealing with occlusions, right? They had this minimum thing, or when we were discussing like this multi-scale loss, all of these things like apply here again. Okay, so now the single most important insight, maybe one of the most important insights of today's lecture is going to be correlation volumes or correspondence volumes. And the reason why it's important is not necessarily because you need to learn about this for optical flow specifically, but I promise you any problem that you actually face in your research that has to relate to vision at some point will probably benefit from this insight. It's a very, very general idea. We've actually briefly talked about this idea before when we talked about plane sweep volumes. Who remembers the discussion on plane sweep volumes? Great, because we're now going to talk about, you. Haha, big mistake. Great. Good. Okay, we're going to talk about it again, so maybe it sticks the second time. So what is a correlation volume? So this discussion is now concerned with, okay, I explained to you what optical flow is, but how do you actually compute optical flow? If I give you 2 frames of a video, how do you actually find out where every pixel in frame number 2 comes from in frame number 1? Okay, so who knows about this stuff? Who has tried to solve this problem before? Has anyone computed optical flow before? Okay, you have computed optical flow, you have computed optical flow with like some off-the-shelf method, or did you actually implement it yourself? Off-the-shelf methods, Raft. Okay, off-the-shelf. Okay, so anyone else? You have computed optical flow. Why aren't you raising your hand, David? Okay, yeah? OpenCV, great. Fantastic, outstanding, okay. So some of you, have you guys computed optical flow before? Yeah, great, what have you used?
I think for me it's like off the shelf.
Like Raft, or what was it, OpenCV, or? Yeah, great. OpenCV, or? And DroidSlam? Interesting, okay, DroidSlam is interesting. Great, so anyone who was using OpenCV, then you're going to learn something today. Next time you compute optical flow, don't do it with OpenCV. OpenCV is lovely, but we're going to talk about something much better today, another off-the-shelf method that works much better than OpenCV. Okay, but good. So how does OpenCV, actually I don't know how specifically the OpenCV algorithm works, but I would venture a guess that it works like this. Okay, so the idea of a correlation volume is like dummy simple. The idea of a correlation volume is we want to build an inference algorithm, so we want to find an algorithmic way of computing optical flow. So for every pixel in frame number 1 or image number 2, we want to find out where it came from in image number 1. Naively, how would you go about doing this? You can say we're going to do it with a search or something, right? You can like pick a pixel in image number 1 and then you do a search over image number 2. And then, I don't know. So it turns out that that idea is very good, but we can formalize it much better by basically this notion of we're going to build an optimization problem such that for every pixel we solve a little optimization problem, and the minimum of that optimization problem, or the maximum, whichever way you define it, is going to be achieved via the correct optical flow. So we're going to do it with optimization. And the key piece of doing that efficiently is called correlation volumes. A correlation volume for images is a 4D volume, so it's a 4-dimensional grid, if you wish, and it's very basic. It's basically just saying for every pixel in image number 1, we're going to compute its correlation with every pixel in image number 2. So what correlation means is dot product. Or you can also compute some notion of distance, right? You can like take the L2 difference. So for every pixel in image number 1, you're going to compute its distance with image number 2. And what does that give you, right? It gives you, of course, a volume of shape, height by width by height by width. It's like a 4D volume. Did I not? I'm going to draw, like I thought I had a textbook. I wanted to be smooth because yeah, Blackboard 2D example, great. It doesn't show up on my screen for some reason. So we have a 2D, we're going to go through this in 2D. I mean, maybe it's kind of obvious, but like I think I just want you to think about it and like appreciate it for a moment. Okay. So this problem doesn't only arise in optical flow, it also arises in things like triangulation, right? Remember in triangulation, you had to solve kind of a similar problem. You wanted to ask for every pixel in image number 1, where does that pixel appear in image number 2? And when you figured out where that pixel appeared in image number 2, when you found that correspondence, then you could use that to triangulate the depth. Do you remember that? Yeah, okay, good. So how would we actually go about doing that? We didn't really discuss that part. So we discussed like, oh, you can do it with like sparse descriptors and then correspondence matching, but there's also a cost volume based approach. So let's say you have image number 1, this is image number 1, and you have the camera like this. And now let's say you have another image like this one. This is camera number 2. So now we're in 2D, right? We're in flatland. So these are two 1D images. So like these are like, let's say, the pixels. And we can draw these rays, right? So through these pixels. Okay, so how would a cost volume look like that we would use to find the correspondence of, I don't have a color. Okay, imagine there was an object like right here. Right, there was an object right there. So that would mean that maybe in these 2 pixels here, that object would appear in these 2 pixels. So in this simple case, the cost volume looks very simple. It says it's basically going to be a 2D cost volume, which is a grid. We're going to take this pixel, we're going to correlate it with this pixel. We're going to take this pixel, we're going to correlate it with this pixel. We're going to take this pixel, we're going to correlate it with this pixel. We're correlating each pixel with each other pixel in the other image, right? And this is going to end up to give you a grid. In this case, the grid is kind of warped because we're drawing it with the perspective transform in it. But fundamentally, you can now imagine you get all these bins, and in each bin you have a scalar value, which is the distance of these 2 things. And now, of course, what will be true is that in this very simple example, in exactly the bins where the object falls in both things, you will get a high correlation score, right? Should surprise no one, right? So here in these bins, you will get a high correlation score. And so in optical flow, you can do the same thing. You can take this thing, you can just compute this correlation volume. Now, I'm going to ask you, if I gave you this correlation volume now, how would you actually go about finding the optical flow? So, yes? Yeah, okay, so in fact, we can also do it here. So this question is identical to me asking you, how do you figure out the depth? Basically, what I'm asking you is, for this pixel here, how do you figure out in this case, the depth, which basically means, or like the correspondence? Well, you would start out with an initial estimate. Your initial estimate might be uninformative. You say, for instance, I don't know, I start with the near plane, or I start with the first point, and then you're basically going along this ray, right? And you're just looking for the maximum correlation. So now you have transformed this problem from like a search to saying, you could basically literally say, you can literally say, I have a free variable, which is the depth. Like this is like I have a variable that I initialize at this value, this is the depth. And now I have an optimization problem, which says, if this is the correlation, so the correct thing makes correlation high, then it means you have this function now that looks like this. And you're trying to find the maximum of this function. So like here, I don't know, it's going to be 0, and then here it's going to be high, then it's going to fall off again. So like now, in order to find the correspondence for a pixel, you're just going to take that part of the cost volume, and you're going to do a search over the height and width axes. Or like you can basically theoretically, you can literally do gradient descent. You can ask, how do I have to change my depth value such that the correlation goes higher? Does that make sense? Good. So what problems do you anticipate when you do that? So like, let's imagine we take exactly this example here with this beautiful goat. And we did that. So like, let's say, for instance, we took exactly this pixel here on the rock, and now we computed the correlation of this pixel with every other pixel in this image. And then we did this thing where we just do the argmax. We just say, okay, the correct optical flow is going to be the point, the flow where the correlation is maximum. What would you expect to happen? Yes?
What would be acceptable? So like the pixel value might change, but there might be like another pixel value.
Correct. So basically the problem will be, even in this image, right? Like, I mean, imagine these 2 images are kind of similar. There's many pixels maybe that have the same color than this pixel. Clearly, right? So in fact, there might be some other pixel that has the perfect colors, and then that pixel might not be the correct correspondence. So here's a few ideas that people have developed over the years to deal with these problems. One idea is an old friend of ours, which is called multiscale, or basically blurring, right? So one thing you can do is let's talk about the first idea first. The very first idea is, of course, one of locality. You say, maybe you can make an assumption. Probably the pixel didn't move much, especially if you have like a video with 30 frames per second, right? From time step to time step, probably every pixel didn't move by a lot. So the first thing you can do is you can say locality. You have a bias towards locality. The second thing you do is you actually do a search. When you solve this optimization problem, you don't only define your optimization problem on the full resolution, where you're susceptible to like local minima, but instead you say, I'm going to blur my 2 images and downsample them, and I'm going to compute a lower resolution cost volume. I'm going to blur my 2 images, like downsample them again, compute another. So you basically build this pyramid of cost volumes. So you have one cost volume at like lower resolution, then slightly higher resolution, then slightly higher resolution. And then that is something that makes you more robust to local minima. So there's all kinds of tricks that people have figured out. But for the next time that you want to compute optical flow with an off-the-shelf method, you're not going to use OpenCV anymore, but instead you're going to use Raft. Okay, so what is Raft? Raft is a paper that we really like at MIT. It's from Jiadeng's group, Zachary Teat at Princeton, who I visited 2 weeks ago, which was really fun. It's actually the reason why Ayush was giving the lecture was because I was in Princeton, and I talked with Jiadeng. It was very fun. So he wrote this great paper some time ago, and this is the figure from the paper. And now I hope you can see what's going on in this paper. Let's walk through it. I think we actually knocked on all of the pieces that we discussed, so I can now explain this piece by piece. So what Raft does, Raft is a supervised method for optical flow estimation. So you assume that you have a data set of ground truth optical flow. Now you might ask, how do you get that data set of ground truth optical flow? We're going to do it synthetically. So in fact, all of these methods are trained on a data set called Sintel. What you see here are frames from the Sintel data set. It's basically a really long movie. It's one movie where you have the ground truth 3D asset, so you can actually calculate the ground truth optical flow. You know how everything moved. And then there's other things where if you have depth, for instance, then it's also easier to compute the optical flow. So there's ground truth optical flow on Kitty, which is a self-driving data set, because they have LiDAR, and with LiDAR it's easier to compute optical flow. So there's some data sets where people have computed optical flow that is pretty good. Okay, so Raft is trained on these data sets. And the way that Raft works is you take 2 consecutive frames of the video, frame 1, frame 2, and now you're going to extract per pixel features with a convolutional neural network. And why are you doing that? Is exactly related to Cairo's question. Cairo asked, well, what if you have appearance changes because of lighting changes and so on? So what the point of these convolutional neural networks is that instead of comparing it in color space, you're comparing it in some feature space. You're basically saying, I'm going to extract features such that at the end my optical flow estimation is easier. So that makes sense, right? So this will hopefully learn to be somewhat robust to color changes. And then what you see here is this dot product. This is what is meant by computing the correlation. So you take every pixel in frame number 1, and you compute the dot product with every with every pixel in frame number 2. And now what you see here is these 4D correlation volumes, which is because they do it at different scales. So they build exactly this multi-scale hierarchy of correlation volumes. And now the last little piece is, how do you actually now, once you have these correlation volumes, in a differentiable way, compute the optical flow? And this piece is a little weird, but it's not that weird. So what you do is, let's go back to this little example here. So now, just for the record, right, each of these is now a scalar value. So you have computed this thing, and you have computed it at different scales. And now what you see here, this iterative thing is exactly this optimization algorithm that we were just discussing, where you're basically doing an optimization over all of the pixels in the other image to find which pixel maximizes the correlation. But if you do this naively, you run into a problem. Let me show you what that problem is. Imagine you have the following situation. Okay, so we have 2 images. I apologize that I always do this with multi-view instead of optical flow. It's very hard. I don't actually know how to visualize it with optical flow. It's much easier to do it with multi-view. But I hope the insight still transfers for you guys. So basically, imagine we had now a ground truth 2D scene that looked like this. We would have 2 spheres floating in space like this. Now, what does our correlation volume look like? I'm just going to draw it, I guess. So correlation volume is going to look like this. So these are the rays from this camera, right? So now we have the same thing here. Okay. So now let's think about the values in this correlation volume. So clearly this value here will be high, right? Because this is the sphere is visible in this pixel, the sphere is visible in this pixel. So clearly this value here will be high, no problem. Great. Same will be true for this. Same will be true for this. So all the pixels where we want the correlation to be high, those pixels will have high correlation. Unfortunately, what happens in this pixel? The correlation will also be high. Because, imagine this is a red sphere, for instance. This pixel here is red. This pixel here is also red because this sphere is over there. So this pixel will also have high correlation. Womp womp. So in fact, and this is something you cannot resolve just with the correlation volume. So, we're not going to go into too much detail. This is actually a very difficult problem to solve, like thinking of a way how to solve this. But here's one naive way how you could think about solving this. So what if you, how could we reject this thing here? Like, how could we reject this correlation? How could we figure out that this correlation is in fact wrong? One way to do it is to look at this image. Like, let's think what that image would look like. This image will look like I don't know, maybe like this. One way is to look at this image and assume that you have a prior from the single image. So for instance, for multi-view, it might be depth, right? Monocular depth. We discussed monocular depth estimation. Even if you just look at one of these two images, you can get an estimate of the geometry of the seed, right? So maybe just from looking at this image here, you actually have a rough, like maybe just from looking at this image here, you have a rough estimate of how far this thing is away and how far this thing is away. So for instance, maybe you know that this thing is closer just from looking at this image alone. So by just finding the maximum along this ray, you can't use that information anyway. So what RAF does is very smart. RAF does exactly what we said before. You initialize your optical flow. In this case, they initialize the optical flow with 0. So they say, my prior assumption is that no pixel moved at all. And then here they actually have a little neural network. And what that little neural network does is it basically does this gradient descent optimization along the ray. It basically does this gradient descent optimization in the correlation volume. It basically looks for the maximum in the correlation volume. But the way it does that is by getting as input not only the correlation volume, it also gets as input the features of the image itself. So in this case, what does that mean? Imagine you now have a little neural network. What the neural network does is imagine it gets this depth variable. This is the depth. So here's a little neural network. It gets the depth as input. It gets a chunk of the correlation volume as input. So maybe imagine it gets the whole correlation volume as input. So it knows where it is in the correlation volume and it knows the depth. And now it also gets the features from this image as input. And now you ask it, like basically conditioned on seeing this local neighborhood in the correlation volume and conditioned on knowing what depth we're at currently, which initially is or optical flow and optical flow 0, and conditioned at looking at this image, please compute an update for the optical flow. So, and now what this thing does is it can look at this image and say, okay, this looks like a car. Cars often move. So this probably has moved. So I should probably assume that this deserves an update. And so it can use the image features, it can use the semantic features that it can extract from the image to disambiguate these flow estimates. Or in the case of multi-view stereo, you can imagine it can use the monocular depth estimates to disambiguate between these two failure modes, right? Just to be clear, right? Like what happens is when you do descent here, if you just do optimization along this ray naively, you might get stuck here because the correlation here is high. But because you can actually look at this image and you know that this thing is further away than just this, you can actually move further and you can reject that local minimum. Does that explanation make sense? Yes?
I think that makes sense. I was just curious as to why we don't expect the feature encoders to be able to do that implicitly. Like why do we need another feature encoder to do the thing that encoded in the features?
Yeah, this is a fantastic and quite deep question, unfortunately. So I'm going to give you the idea, but if you don't get it, because it took me some time to get this, but maybe you're much quicker than I am, so let's see. So the problem is tricky. So the question is really fantastic. The question is, why don't the two feature extractors already encode why don't the two feature extractors encode, for instance, the depth in these 2 pixels such that this correlation will be low? That's the question you're asking, right? So technically you can say, well, if this monocular depth, if this thing can look at this image and it can estimate the depth, then why couldn't it just write the depth into this feature, write the depth into this feature, and then it knows that this is the only viable? Okay, so maybe some of you know why that doesn't work. Think about it for a moment. It's unfortunately it's a little tricky. So why does that not work? Why, in this specific case of depth estimation, why can the two feature extractors not encode features for this pixel here and for this pixel here such that this correlation is low and this correlation is high? Okay, so the reason is that the thing that you need to disambiguate these two cases is the depth, but this feature encoder doesn't know about the camera pose of this feature encoder. So what could this thing do? This thing here can encode this distance in the in this feature, for instance, right? It can estimate the depth. It can say, okay, this distance. And this thing here can in turn encode this distance in the feature. But these two distances are not in the same coordinate frame. So these two distances do not allow you to disambiguate these two cases. The only way in which you could use these two distances is if you took this distance and you transformed it into this coordinate frame, then you could compare it to this distance and realize that they're not the same, and then you could reject it. But because they're not in the same coordinate frame, you can't actually compute them you can't actually compare them via correlation. You would first have to apply the Kerber transformation. Does that make sense? Okay. So for the optical flow, what is the equivalent for optical flow? I actually don't know off the top of my head. I'm not even sure if this kind of ambiguity, this kind of ambiguity might also exist in optical flow, but I would have to think about it. Yes? Because the transformation might be different for every frame. Like I give you two images, right? And the two images might have this baseline, or they might have this baseline. But you're right. Like if the baseline is always fixed, then the encoder could learn to encode this camera transformation in there. So actually, yeah, good point. If the encoder either knows about the camera pose and it has a smart way of like doing it, which is questionable, either if it knows about the camera pose or if the camera pose is always fixed, then it could solve it. Yeah.
Because I understand they're doing the correlation with feature vectors.
No, they don't use the color, but I guess this is a ResNet, and so or a UNet, and so like if the color was useful, it would just skip the color through for it to compute the dot product. Good question. Any other questions? Great. So like okay. So then just to be clear, so then this starts with 0, and then we are skipping some details. Go read the paper if you want to learn more about it. But then it basically runs this optimization algorithm for a fixed number of times. So there's like 12 or 15 or something, and then at the end it just outputs the whichever flow it has estimated until then, and that's the optical flow, and then you supervise it. And then you train it end to end. Does that make sense? I think I have a detailed figure for how the update step works, but I don't know if you want to get into it. Yeah, actually, so this is the update. So you can basically, so there's this is the neural network that computes the update for the flow, and it takes as input the correlation volume, and then it takes as input the current estimate of the flow. And then the context, that's what they mean by the image. But I think you should read the paper if you're interested. But basically, long story short, next time you compute optical flow, don't use OpenCV, use Raft. It works much better. It is actually quite shocking how well it works. So the reason why it's quite shocking is because it's only trained on synthetic data, and maybe Kitty. I think it's trained on synthetic data and Kitty. But because there's no ground truth optical flow, right? If you go around with a camera, you can't capture a ground truth optical flow. And even though it's trained only on synthetic data, it generalizes pretty well to real-world scenes. So it works pretty reasonable. So in fact, if you remember FlowCam, when we discussed FlowCam, Raft is the optical flow estimator that we used, and it worked really well for camera pose estimation. Okay, does that make sense? More questions on Raft? Okay, so now you have an idea of like how to compute optical flow. You can use OpenCV off the shelf or Raft, and you have an idea of how these algorithms work. So just for the record, like you don't need to do this with a neural network, right? You can also just implement optimization algorithms on top of these cost volumes. And these have no learned parameters. You can just hand write this optimization algorithm. It just then will run into these these local minima, and it's really hard to make it robust to like lighting and stuff like that. So this thing is just like is more robust. Okay, so now we discussed optical flow. There is of course the 3D equivalent of optical flow. Optical flow is 2D flow fields. The 3D equivalent is called scene flow, and scene flow is just a 3D flow field. So should surprise no one. So we can just do the same thing in 3D. So instead of describing for every 2D point, how did this 2D point move, now for every 3D point, we describe how this 3D point moves. And we again describe it with a little flow vector. Make sense? Excellent. Okay, so here's a fun fact, which we already discussed when we discussed FlowCam briefly. But optical flow is the projection of scene flow. This should be intuitive. So if something, imagine you have a camera. Imagine you have a camera, and you have an object that moves. So the scene flow might look like this. So the object just moves from left to right. Actually, we're going to draw everything. So the scene flow is actually a scene flow field like that, right? It's like it's a flow field for the whole thing. And now you capture an image of it, right? So if this is a scene flow vector, then the optical flow is, of course, just the projection So this will be the optical flow. So like the projection of this scene flow is the optical flow. And noteworthily, of course, the same is true, the same as for rendering is true. Like, of course, if you have a scene flow field and there's a part of the scene that is occluded and you project that, then you don't see it in the image. So of course you have to, this projection has to be occlusion aware. Makes sense, right? So, but for every point that is visible, the 2D point is really just a projection of the 3D flow. And as we will see in a moment, we can exploit that quite heavily. We exploited it already in FlowCam, but we can exploit this. So in other words, we can use, so I already told you that it's pretty easy to compute 2D optical flow, or like some of you have even done it already. And actually just to add one more sentence to this, optical flow is one of these things that work pretty well. So like if you have a practical problem where you need to compute the optical flow, it's not like, this is hard. It's like it really works reasonably well. So like it really, like 80% of the time, it's just solved by downloading Raft and running it on this thing. So like optical flow is like really robust. It generalizes really well. It's like actually quite good. So because that is true, in other words, you can kind of treat it as pseudo-ground truth. So knowing that optical flow estimation is really good, you can actually treat the 2D optical flow that you compute on a video as a constraint when you're solving for the 3D scene flow. So if you're saying, okay, I have a video, I want to reconstruct the 3D motion of parts of the scene. In other words, I want to reconstruct the 3D scene flow. Then you can just assume that the optical flow is good. You just pre-compute the optical flow, and the optical flow via this correspondence will give you a constraint on the 3D scene flow. So you can use the optical flow to supervise the scene flow estimates. Does that make sense? Right. And then there's like a bunch of interesting stuff going on that is maybe not obvious. So the first interesting thing is that if you think about optical flow fields are really complicated. And let's talk about why that is. So imagine the scene would be perfectly static, and I just took a camera and I just moved it like this. What would the optical flow look like for points that are closer to the camera versus points that are further away from the camera? Yeah. Right, so basically points that are closer to the camera move faster, and points that are further away from the camera move slower. Now think about this optical flow field for a moment as a function. So like literally think about it as a flow field. Like, I don't know if any of you are like electrical engineers, then you might have taken like electromagnetic field theory or something like that in undergrad, where you actually deal with like fields and vector fields and stuff like that. But just think for a moment about this actual field as a function. So it's like this continuous vector field that maps every 2D coordinate to a flow. And if you think about the 2D flow field, think about the properties that it has. It has like kind of a smoothness property because the depth maybe, right? Like if you think about the walls, like the depth of the wall changes smoothly. So for all the points that lie on the walls, the optical flow will change. Like the ones furthest back will have the smallest flow. The ones closest to you will have the largest flow. And then the magnitude of the flow will decay as you get from the points that are close to the points that are further back, right? Okay, so that's easy. So there's like a smoothness thing going on. And then you have a thing going on where if there's a disocclusion, then the optical flow changes drastically, right? So like, for instance, for all of the chairs, there's like this depth discontinuity. At all of these depth discontinuities, the flow is like changing discontinuously. It's like jumping from being small, jumping to be really fast. Now think about the scene flow. So think about the 3D flow that is actually going on. So imagine, okay, I'm going to ask you the same question again. Imagine the scene was static, and I'm moving the camera, and I'm moving the camera like this. And now, thinking about the scene flow is a little bit weird because the scene is moving, but imagine for a moment that the camera would be static and the scene would move, which is hard. Like just imagine this camera is static here and the whole room moves relative to the camera, okay? So what is the property of the scene flow field? What can you say about the scene flow field? Right, it's explained by a rigid transform. In other words, every point in the 3D scene flow field has the same scene flow. The 3D scene flow field is, as long as there's no rotation. If there's no rotation, if there's just translation, the 3D scene flow field is static. It's constant. Everywhere, it has every point in the 3D scene has the same flow. But the moment you project it, because of the projective transformation, you get all of this weird stuff where like now it goes from being constant everywhere to being like discontinuous and piecewise smooth, which is like much worse, right? So the 3D scene flow field is almost always much simpler than the 2D flow field. So what does that mean? For instance, let's take this example of this outdoor scene. imagine that the camera wouldn't be moving and all these cars are driving around. The optical flow, of course, the optical flow, even for a single car, is actually not straightforward. So for instance, if you take the optical flow of the point that is here, that optical flow will be different than the optical flow like on the other side of the car, because that other point is further away. But if you think about the scene flow, the whole scene flow of the whole car is going to be explained by one rigid transformation. So if there's some rotation going on, it's not quite straightforward, but imagine for a moment the car is just driving forward without any steering. Then the whole, again, it's all the translation vectors will be the same. So the whole car is moving at once. So in other words, the scene flow field usually has a property of piecewise rigidity, which means that if you take the scene flow, you can usually chunk it into pieces, and each piece is moving piecewise rigid, which means it's explained by one R and T, like one. We're discussing these camera transformation matrices. It is as if each object is transforming according to one camera transformation, basically. Different from the optical field. So this is another constraint that you can use. Does that make sense? Questions? Great. And now we come to that exact point. So so far I was like kind of telling you, imagine that the whole room is moving, constant, like it's just translating. Then like the scene flow field is constant. The scene flow field is constant. It's just one translation vector everywhere. Imagine something is rotating, or imagine the cars are doing a curve. Then unfortunately it's not true anymore that every scene flow vector will be the same. They will be different, because if you have a rotation, like there's a rotation of this thing here, right? Even though all of these parts are rigidly connected, it's a rigid, like the whole thing can be described by one rigid body transform, in other words, by one rotation matrix, right? The motion of this whole thing can be described by one rotation matrix from time step to time step. Make sense? Yeah. Even though that is true, if you look at the flow vector, so how is every point moving on this thing? Every point, of course, is moving differently. Like this point here has a much larger magnitude flow vector than the point in the center, which has a 0 flow vector. And that is the notion of a, that is the notion of a translation field. That's the difference of a translation field to a rigid body motion field. So if you look at this translation field, so imagine we're in optical flow right now. So like you map every point here to a single 2D translation vector. These 2D translation vectors will be different for every point along the blade of the thing. And at the tip of it, they will be large. At the center, they will be 0. But then you can also say we're considering rigid body motion fields. So what is a rigid body motion field? It's a field that maps every point in the image, not to a translation vector, but it's mapping it to a rotation and a translation vector. And so in other words, every point is mapped to a representation of the rigid body motion of that point. And if you think about that field, actually this should be SE2. So this is now a field that maps every pixel coordinate to one rotation, 2D rotation and one translation. If you think about that field is constant across the whole blade. Does that make sense? So it's just a kind of. So why am I explaining this? I'm explaining this to you because it turns out there's ways of regularizing. So if you parameterize the optical flow field like this, or the scene flow field like this, so you parameterize it as a field that maps every point, not just to a translation, but actually to a rotation and a translation, then you can, for instance, add a regularizer that says, I want that field to be piecewise constant. So I want that neighboring points generally have the same rigid body transformation. And then you can take the scene flow field and you can actually write a regularizer that says it should be piecewise constant. Versus if you parameterize it just as a translation field, then the translation field is, again, it's just piecewise smooth. It's not piecewise constant. It's just piecewise smooth. So some regularizers get easier to express in one representation than the other. Make sense? Great. Great. So here's a few papers that try to solve for these things. So here's a paper, deep rigid instant scene flow. So this is important in self-driving, as should surprise no one, right? In self-driving, it's really important. In self-driving, you want to estimate your own motion. You want to estimate how far stuff is away. And you better estimate how stuff is moving to anticipate how it's going to move in the future. So here's a paper, for instance, that takes stereo as input. And then from stereo, it's kind of like, these are all variations of the self-supervised monocular depth and pose estimation thing. So here's a paper that takes the stereo depth and then does exactly what we just discussed, actually. So it computes optical flow in the first thing. Then it computes like semantic segmentation. I think that's pre-trained. and then it computes visual cues, or in other words, like visual features. And then it uses the semantic segmentation to mask out the flow, and it uses the features to compute like features. And then it has a differentiable Gauss-Newton solver, which is basically a solver that solves the problem that we just discussed. So it's going to say, okay, now I have the optical flow, and I have the depth maybe, and I have the segmentations, and now for each piece, I'm going to solve for one rigid body transform that explains that one piece that is moving. We're not going to discuss in detail, but like this, I'm just giving you an example for like a paper that does this. So you can also do it self-supervised, but whatever. Okay, so the only other paper we're going to discuss is Raft 3D, because Raft is so much fun. So, yes?
I think like all of the examples we've talked about so far is like either the camera is moving or on the scene.
Yeah.
So how would you like approach a problem in which things are moving while the camera is moving?
Great question. Yeah, so the question is, so it seems that all the examples we discussed so far, either the camera is static and the scene is moving, or the scene is moving and the camera is static. The truth of the matter is that fundamentally these two things are not that different. So because the motion of the camera you can think of as like not a privileged motion. It's like not any different from any object in the scene moving. Let me explain. So exactly this example that we just discussed, the camera is moving but the scene is static. You can always flip that around to saying the scene is moving and the camera is static. So basically when the camera is moving as well, you can imagine that you just have to solve for the motion of one more object, and that object is the static background. And so the motion of the static background relative to the camera, that is the camera motion. Does that make sense? And yeah, like I already mentioned this thing before. So when you're sitting in a train car and the train car next to you starts moving, right? What happens? Like you actually notice this exact thing, that like your own motion is not privileged. Like your brain gets confused. The thing that you just discussed is exactly the thing that your brain gets confused about, because you're sitting in the car and now something starts moving. And notice that really what your eye is measuring is 2D pixel motion. So your eye is basically measuring more or less, the only thing that your brain can get from that is optical flow. So your brain is basically observing that a large part of your visual field is probably suddenly moving. And what is your brain doing? Your brain is saying, oh, if a large part of my field of view is moving, then usually that means that I'm moving. And so it's explaining the motion of the train car with your ego motion, and then you feel like you're moving. And then you get confused. Actually, fun story. I was with a friend at MAS MoCA over the weekend. MAS MoCA is like an arts museum which you should all go to. It's really cool. And it was really fun. We were like, he's a collaborator actually. So we're going to the parking lot, and we were pulling into a parking space where two other people were about to pull out. So he pulls into the parking spot, and then he shuts off the car. In front of us, there's another car. So like he parks into the parking spot. In front of us, there's another car. He shuts off the car. And then at the same time, both of the cars next to him start moving. And he loses his shit because he's like, oh my God, the car's moving. And then he like pulls the handbrake, right? Because he got this strong feeling that he's moving. He's the one that's moving. Because of course, that's how your brain explains it usually. And then I thought that was very amusing, because that's actually the exact thing that inspired this FlowCam paper we discussed. So yeah, and like I hope this answers your question. Basically, these two things aren't all that different. So you can always treat the camera motion as just another example of the scene moving. I don't quite understand the question. So when is it harder or easier to solve for what, one or the other?
Like, is there an order in which you should solve?
Ah, great question. Yeah, so this is an open question. So which we're kind of, yes, like this is a good research question. If you want to learn more about that, we can talk about that offline, but this is actually an interesting research question. So it does turn out that there is a relationship, like if you wanted to, like, it is clear that sometimes you might be interested in the motion of objects relative to the static background. And in order for that, for you to do that, you first have to figure out which part of the scene is the static background. And in that case, you need to solve for the camera motion first. But I don't, unclear of like, it's actually not straightforward to identify which of the motions in the scene is the ego motion, which again, you know, because even for you, it's not straightforward. Happens sometimes that your brain gets confused about like which motion is the ego motion and which motion is the scene motion. Yeah, Good question. Fantastic question. More questions? Cool. Oh, wait, we jumped again. Oh, no. Raft 3D. Okay. We're going to talk about Raft 3D for a moment. So we already talked about Raft. Now we're going to talk about Raft 3D. Raft 3D is kind of like a follow-up paper to Raft, and the point is to solve for scene flow instead of solving for flow, as the title Raft 3D might suggest. So the assumption of Raft 3D is that you have as input not only the image, but also the depth, which is obviously a strong assumption. So generally, right, you might be interested in solving for the scene flow, even though you don't have the depth. Oftentimes, you might actually be interested in solving for the scene flow just from the video, but that's not the problem that Raft 3D is tackling. That's a very hard problem. So what Raft is doing is just saying, okay, we have images and we have depths. So image 1, depth, image 2, depth 2, image 1, depth 1. And now just to go through the motions again, right, they do the same thing. They extract features for both of the things. But now look carefully at what is going on. What they're doing here is they're telling you that they're solving not for a 2D motion at every pixel, but they're instead solving for a SE3 motion at every pixel. SE3 is rotation and translation. So they're actually solving for a 3D rotation and for a 3D translation at every pixel coordinate. And actually, sorry, it's not at every pixel coordinate, it's at every 3D coordinate. And that is easy, that is, in this case, it's easier because you already have the depth, right? So for every pixel, you already know the 3D coordinate of that pixel. And so now you just have to say, okay, like now, just give me the 3D rotation and translation of that pixel coordinate. And the way this works is basically kind of the same. You build the correlation volume again. So you take every pixel in frame 1, you take every pixel in frame 2, you get the correlation. And that again allows you to get this optical flow, right, as we discussed before. So it allows you to compute the optical flow just by a Raft, for instance. And now what you do is you say, okay, I want to explain this correlation volume. So I want to explain which pixels, I want to not only find which pixels are correlated with each other, but I also want to use the depth to solve for the 3D motion of all of these things. So in other words, I say, because my scene is usually piecewise rigid, because I know that my scene is usually moving piecewise rigidly, I don't just solve for the optical flow, which has these not so nice properties of like not being smooth and stuff, like being discontinuous and stuff like that. Instead, I'm just going to directly solve for the SE3 transform of every object. And that's what you're seeing here. So they're jointly solving for the optical flow. But actually, because they have the depth, it's possible to go to not only solve for the optical flow, but then immediately also solve for the 3D motion of each object in the scene. And we're not going to go into too much detail. I just want to make you aware of the existence of this paper, which is fun. This one doesn't work as well. So like if you actually have to solve for scene flow, good luck. Optical flow really works. This one doesn't work as well, but like it's definitely a good idea. And it's actually very related to DroidSlam. You said you used DroidSlam before, right? So DroidSlam is by the same authors, and DroidSlam uses the same backend, and they just actually solve for the camera motion instead of the motion of every piece in the scene. Okay. I think we discussed this to death now. Actually, slower than I anticipated, which happens rarely. Okay, so takeaways. Scene flow is the 2D optical flow is the projection of scene flow. Scene flow has all these nice properties, optical flow not so much, and you can get away with, or you can gain like nice properties by solving for the rigid body translation or like the rigid body motion instead of the translation. Okay, now we're going to talk about 3D dynamic reconstruction in the framework of inverse graphics. So how can we use all these insights? So we discussed initially that we basically reconstruct this nerve, where we have, forget about the v direction for a moment, we just have x as input, and we have the time as input, and now we have the density and the color as output. And now we want to do exactly that. We want to reconstruct a 3D dynamic, like a 3D scene that is moving, like this scene of this child. Right, so here's the child moving. What you want to do is you want to be able at every time step rendering novel views. So you would like to be able to move the camera, so 3D reconstruction. You would like to be able to fix the camera and then just interpolate time. So basically this is like a slow-mo effect. Or you would like to do both at the same time. So you would like to, after you have reconstructed this video, you would like to be able to move the camera while you play the video. So in principle, this should be possible, right? Certainly you can do that. You can watch a video and then you understand the 3D geometry of the video. You can imagine of like what that video might look like from a different angle. Okay, so what's funny? Nothing. I also want to laugh. I'm sorry. Fine. Okay, how? We're now going to use all these amazing insights we have just discovered. what we're going to do now is we're going to say we have our function here. Now it's this is our nerf basically. So it takes as input an x coordinate, and then it takes as input a I don't know why I put d there. It's actually, imagine it's no, of course. So this takes as input x, that's a 3D coordinate, ignore the d, and then I is just the frame index. So I is like the time. So like you can replace I with t in your mind. Okay, so ignore the d. The d is again the view direction, but let's forget about the view direction. So it's just x. So you have as input to your 3D field, you have an x coordinate and you have a time coordinate, which is I. Okay, now we're going to map that to a color and the density, just like with the normal nerf. So that allows us to do volume rendering, right? So far nothing new. Make sense? Okay, good. But now here comes the trick. We're also going to map it to a flow vector. We're going to map every 3D space, we're going to map every space-time, not only to a color and the density, but we're also going to map every 3D space-time, like every space-time coordinate, to a flow vector that tells you where did that 3D point move to at the next time step, and where did it come from in the previous time step. Does that make sense? Okay, that's great. And so just to see what that looks like, imagine now the camera is moving and the scene is moving, like this child is doing stuff. So now what you get is that when you shoot this ray, at every point along the ray, when you do volume rendering, right, not only do you have the color and the density, but you also have this, also have the scene flow, this correspondence vector, that tells you where did this point move to in the next time step. And now something magical happens. Because now you can actually use this additional flow vector to use it as a constraint of your optimization process. Because now you can say, okay, I want to make sure that the radiance field at time step t can always be explained by the radiance field at time step t minus 1 after I apply the flow. So you basically, you can add a loss term. You can just add a loss term to your loss, right? That says that I'm penalizing that if the flow vector, I'm penalizing the difference between the color and the density at time step t to the color and the density at time step t minus 1 according to the flow that I'm solving for. So in other words, you're trying to solve for a flow such that you have this guarantee that for every time step, for every point in the scene, you have a continuous motion through the scene. Does that make sense? Great. Okay, yeah, whatever. Yeah, so basically you're just saying exactly this. You're just saying that the color at time step I should be you can do this for the pixel coordinate, right? But you can also do it for every point along the ray, like you're seeing it here. So the color at every point along the ray should be identical to the color at in the previous time step flown by the scene flow vector. Yeah, okay, whatever. This is and here's the optical flow constraint. So now you're solving, right? Now you're running this optimization problem. What is this doing? It's solving for the color and the density at every 3D coordinate at every time. It's also solving for the 3D motion at every 3D point in time. And now that is the scene flow, right? So it's basically, that is the motion in 3D. And now this beautiful constraint comes into play because you can easily compute the optical flow. The optical flow is cheap and reliable to compute. So you know that when you render the scene flow field, so when you render the scene flow field, that when you project the scene flow, it should match the optical flow that you pre-computed. And now you can use this as a constraint. And intuitively, what you can imagine this does is it makes the optimization problem so much easier. Because just to be clear, right, like what we're actually doing is like a very, very hard optimization problem because we're, imagine, I don't know, I'm not sure if I can do a good job at drawing this. I can try. So imagine this. Imagine you have these two objects. One object is static, so this thing is not moving at all. This object here is moving to the right, so maybe it's like that, and then at the next time step it'll be here. And now you have, let's say, let's say the camera is not moving. Yeah, let's say the camera is not moving. Okay. Right. So now, if you look at the images that this captures at time step t, the image will look maybe like. The image might look like this, so it's like a little box, and then it's occluded by the ball. So this is at time step t, and then at time step t plus 1, the ball has moved, and now maybe the box is not occluded anymore. Does that make sense? Okay, good. And now what are you trying to do, right? You are given just these two images, And given these two images, you're trying to solve for the density at each of these points, like the color and the density at each of these points, color density, as well as the flow vector at each of these things. And that's very hard. And it has all these local minima that we discussed, right? We discussed the stuff like you have to apply blur in image space if you want that the gradient is well defined and stuff like that. Do you remember that when we discussed? Yeah, okay, good, so I'm nodding. Okay, so the same problem arises here again, but now imagine you kind of have a cheat code. The cheat code that you have is that you know that after projecting, this 3D scene flow has to map the optical flow. So you can compute the optical flow from these two frames, and then the optical flow will tell you that like there was motion here, and so you already know that somewhere along this ray something must have moved. And so this constraint makes it possible to actually solve this optimization problem, where in practice without the optical flow it basically wouldn't work at all. Yes?
Why do you need both the optical flow constraint and the one you showed originally?
Yeah, good question. So you don't need it. So technically the question is why isn't this cycle consistency enough? So why isn't it enough? Sorry, not cycle consistency. Why isn't it enough to say that the color and density at the 3D point should be identical to the color and density at the previous time step modulo the translation or the flow? And technically it should be enough. It's just that empirically your optimization falls into a local minimum. So for instance, what will happen is it'll, I don't know, maybe the flow vector, imagine for instance one failure case is the flow vector is just huge and it points at a random point in the scene. Right, like, and then what? And then you're like, okay, so your constraint might be true, but like the flow is okay. And then you might want to do all kinds of regularizations. You might want to say the scene flow is smooth over time. So at every time step, the scene flow can't change too much. And then you might have as additional constraint this, and this constraint gives you like a lot. So this constraint basically actually makes this problem tractable, where without it, it's basically not tractable. So yeah, go ahead. Yeah, there's also cycle consistency, which I conveniently skipped. But now you asked about it, so now we have to talk about it. So the cycle consistency constraint is that basically just saying that if you are at time step t, I already told you that this method is at every xyz coordinate, xyz t coordinate, so at every space-time coordinate, it gives you the flow to the next time step and the flow to the previous time step. And the cycle consistency is just saying that at xyz t, you get a flow, you get this flow, and that flow should be identical to the backwards flow from the previous time step to that flow. So those two should be identical up to flipping of the sign. That's the cycle consistency. So you're just saying that yeah. Does that make sense? Any questions? So this kind of almost works, but it doesn't actually. So like this, as I said before, like this, when does this work? This works basically if you have small camera motion and you have small scene motion. Then these kinds of methods work, then you can kind of make it work. So if I move the camera a little bit and you were nodding your head just as you were just doing, then we could maybe reconstruct it, and then we can wobble the camera around and you could be nodding your head. That'd be good. Yeah, okay, whatever. Okay, so here's, no video? Okay, yeah, more results, skip it. Okay, maybe not. So here's the result, right? So you can like, do this kind of stuff. And so I can tell you right now, so this looks pretty reasonable, so you might be like, yeah, we're done. But in practice, the reason why these scenes work and maybe the other views don't work is because when you look at these images carefully, the camera is moving fast relative to the motion of the person. So the amount that the person is moving is relatively small relative to the amount that the camera is moving. So essentially what you get from that is it's like, imagine the limit of this. The limit of this is a static scene. Like if the camera was moving infinitely fast and it would take millions of images every second, then for all intents and purposes, you have like, it is as if the scene was static. You have multi-view observations of a static scene. And so if you look at these images that were captured here, right, the camera is moving relative, like there's a lot of camera baseline relative to the motion of this person. The person is moving relatively slowly relative to how fast the camera is moving. And the same is true for this other scene. And in this case, this problem is tractable today. So if you have lots of pictures where the camera is moving relatively fast relative to the motion of the scene. In the general case, of course, that's not true. In the general case, the camera is moving slow. Yes?
The regime, is it almost comparable to doing like you're using a few views and then just adding a temporal constraint?
Yeah, let me think. Yeah, so it's certainly related, but in the case of PixelNerf, right, you usually generalize across many scenes. So this one is optimized for each video separately. So here you're solving for, yeah, this is a good question. So to clarify, this one is solving for one reconstruction per scene. So there's no learning here. So this is really just solving this optimization problem.
Or I guess like the few shot, or the single view nature.
Oh yeah, good question. Yeah. So you're asking in the more general case where the camera is not moving fast relative to the motion of the scene. Yes, you're right. In that case, it is kind of related to the idea that generalization might help you, because if you would have a good, like, it is good to think about that, like, okay, for all the background, okay, let's imagine you're moving and my camera is moving slowly. Then for all of the points in the background, it is indeed the case that that is exactly as if you were just overfitting a single scene. But when you're moving, for each of your poses, my camera has only one picture of your 3D geometry at one pose. And in that case, it is useful to think, maybe generalization would help with that. Because in this case, I'm basically saying, okay, at every time step, for everything that is moving in my scene, I really only have one image to reconstruct the 3D geometry. That is a good way to think about it, yeah. Does that question make sense to people? So basically, good way to think about dynamic reconstruction is it is as if you only have a single picture of every move, like, it's kind of almost like the single image 3D reconstruction thing. For every object that is moving in the scene, it is as if you only have a single observation of that object and you have to do 3D reconstruction from that single image. Because for every pose of the object, you only have one single image as your overtime. Cool. We have a few more minutes. I'm not sure if we're going to get through that. In case not, we're going to continue next time. But, I mean, this is actually, as we're going to see in the next lecture, this is actually has turned out to be the reliable way of doing this reconstruction. Here's another way that was more popular about a year ago, 2 years ago, of thinking about this reconstruction problem. So notice here, we are reconstructing a separate radiance field for every time step, right? Because our radiance field is taking as input x, y, z in time, so it's taking the time coordinate as input. So it is as if we had one separate 3D reconstruction per time step, and all we've done is we added the scene flow thing to regularize them to be consistent over time. But of course, there's another way to think about this. The other way of thinking about this is to say, well, that is kind of stupid. As we said before, technically, when I'm moving, like, it should be possible to reconstruct me only once and then express every time step as a deformation of one Vincent. Okay, yeah, whatever. So this is called a canonical representation. And actually, yeah, it's a fancy word, but all of you probably know this. Like in video games, for instance, right? Like obviously, when you have a character, you don't model the character separately for every time step, like for every pose. Actually, you model the character usually in a T-pose, and then you express every possible pose of the character as a deformation of the T-pose. So this is this idea. So the idea is basically we're going to model a single canonical 3D reconstruction. So we're going to represent our scene. We're going to only reconstruct the 3D scene once, and then over time, we're just animating that, we're deforming that 3D scene representation, this canonical 3D representation. So that means we're solving for one static 3D reconstruction, and then we're solving for a flow field. And the static reconstruction doesn't have to depend on time, because it's time independent. And the only thing that has to depend on time is the flow field. And the flow field is now different from the flow field we had before. Previously, the flow field was giving you the flow with respect to the previous and the next time step. Now this flow field gives you, for every time step, the deformation with respect to the canonical pose. So it's like now saying, I don't know, if I'm like that, then it's the deformation relative to the T-pose, for instance. There were like 16 papers that came out at the same time that did exactly the same thing. Actually, it's just 4. One is missing. I don't know which one is missing. So Ayush, you know? Here's Ayush. So the one that is missing is actually the one from MIT. Yilin also wrote one paper that does this as well. So there were 4 papers that did this at the same time. I'm not sure why I don't have it here. But like, yeah, so pretty straightforward. So it's exactly the idea makes perfect sense. You just have a static reconstruction, which is this canonical space here. So this is really just a function that maps an x by z coordinate to a color and the density. And then if you want to deform, if you want to express the scene at a different time step, all you do is basically you you have a function that maps x, y, z, and t. So the scene at that time step to a flow, and that flow then tells you where to go look in the canonical thing. Whatever. Okay, and like then on the right you can see the inputs, on the left you can see the reconstruction, and this looks really cool, but as you might be able to tell from the input views, this again has this rather stark constraint that it really only works if you have a shit ton of observations over for every time step. So I think, in fact, you probably have several observations at each time step. So this kind of stuff is it is useful in one specific case. It's useful in one specific case where you have hundreds of cameras. When you have like hundreds, and just to be clear, these things exist. They're called light stages. So for instance, Meta has a light stage. MIT doesn't have one at the moment, I think, but like light stages are a little globe. I'm sure you've seen them. They're like little globes where there's like thousands of cameras pointing inwards, and then there's like maybe thousands of light sources, and then you can walk into it, and then you can move, and as you're moving, you're being captured in real time by like thousands of cameras. It's just generating like terabytes of data every second. But then from that kind of video, you can reconstruct something like that, because you have like multi-view observations at each time step, and then solving this optimization problem is relatively easy. Okay. And you can do it with an SE3 field, so instead of mapping every point to a translation, you can map every point to a rigid body motion, and then you can do all of the things we discussed, like you can regularize it to be piecewise rigid, and all that stuff becomes easier. Okay, yeah. I don't want to talk about that, whatever. Yeah, so there were basically lots of variations on this where like people said like, oh, actually feeding the time as input, that's not expressive enough. My neural field is not going to be able to do that. So instead of feeding the time as input, we're going to have a separate latent code for each frame, and then the latent code is like pairs of all kinds of shenanigans. But I don't think any of this will be. Yeah. So these are dynamic 3D reconstructions. Kind of works. Yeah. So I think actually we wrapped up in time. Yeah. One more thing we can talk about actually for. So like now we discussed canonical representation, as we discussed like these per time step representations that are regularized by time step to time step flow, and then we discussed the idea of having a canonical volume that is being deformed. Now we're going to discuss one more fun part, which is a different problem, that problem is the one of just reconstructing separate representations for the static background and the dynamic foreground. So here's a paper from our friend Andrea. It's called D2Nerve, Self-Supervised Decoupling of Dynamic and Static Objects for Monocular Video. And what they do here is they say we have a video where the camera is moving, and now what we want to do is we want to have one separate 3D reconstruction of the static background and one separate 3D reconstruction of the stuff that is moving. And the way to think about this is as a generalization of the idea of background subtraction. Hello. Hi. Fair enough. So background subtraction is this is only like a 2-minute discussion, so it's great. Background subtraction, what do you do if you have a video? You take the mean, like you assume the camera is static and only stuff is moving. So this is often done for traffic cameras. You have a traffic camera that's pointing at a highway. The camera isn't moving, only the cars on the highway are moving. You take the video stream, and then you just take the mean of all the videos, like of all the video frames over time. So you just capture like 1 million frames and you take the mean. Or you take like a robust mean or something. What you get is basically the background, right? Like the mean of all of the frames, like all of the stuff that is moving over time will average each other out to like a blurry thing, and what is left is the background. In practice, you don't take the mean, you like do something to like kind of try to filter out the stuff. But it's relatively easy to detect which stuff is changing over time. Okay, so, and then you can say, okay, so now if I have a new frame of a new video, what I can do is I can subtract that background. I can take the static background that I have and I subtract it away from my current frame by just literally taking the difference between my current frame and the background that I have calculated. And that will allow you to basically segment out everything that was moving. And then this was an early approach to like segmentation. Right? For instance, if you are on a highway and you have a highway camera, then you can use this and you basically get out a mask where you have these islands of cars, and then you can run a simple segmentation grouping algorithm to get the cars that are moving. So this idea of background subtraction, you can generalize it to saying, okay, now I'm going to, if I have a video where something is moving, I can say I have one static 3D reconstruction that is going to stay constant over time, and that is kind of my background reconstruction. And then I'm going to explain every frame by compositing